This training module will introduce you to the working principle of Coriolis mass flow meters. Upon completion of this module, you will be able to describe how mass flow is measured, explain how density is measured, and identify the advantages of the Coriolis mass flow metering technique. Gustave Gaspard Coriolis found out that Newton's formulae of movement are also valid in rotating systems, if one considers the Coriolis force. Experiencing the Coriolis force is a question of the inertial system. Just imagine a rotating disk. If the viewer stands away from the disk, he will see the disk rotating. If a ball in the center of the disk is accelerated to the outside of the disk, the viewer will see a straight line of movement and the disk rotating under the ball. It is different if the viewer is located on the disk. In this case, he would not see the movement of the disk, since there is no relative movement. The accelerated ball would not move along a straight line, but would have a distorted path and move along a curve. This distortion is caused by what is called the Coriolis force. This force is a general force in physics and can be found in many phenomena, such as the rotation of low-pressure systems in the weather or at Foucault's pendulum. The magnitude of the force depends on the mass of the ball, on the rotation speed, and the speed of the ball. The direction of the force is defined by the vector product of the two velocities involved. A sideward movement of the ball could of course be removed by installing a tube around the ball. In this case, the ball would be forced along its track, but the Coriolis force would nevertheless be present. Depending on the tube and on the force, the tube would be slightly distorted or bent by the Coriolis force. This basic idea was the foundation principle of the first Coriolis meters, using a tube rotating 360 degrees, slightly distorted by the Coriolis forces, with the degree of distortion being measured. However, since 360-degree tube rotation is quite impractical, more practical methods of harnessing the Coriolis force were soon developed. The solution was a tube oscillating up and down and not performing a complete 360-degree rotation. In case of no flow, the fluid, or balls in our example, would not experience any Coriolis force. In the case of a moving fluid, the Coriolis force affects the fluid and consequently the tube, bending it down or up. The direction of the Coriolis force depends on the direction of rotation present at a particular moment of time. In the left half, the instantaneous rotation is anticlockwise. In the right half of the tube, the instantaneous rotation is clockwise. Consequently, the tube is bent downwards on the left and upwards on the right. The relative distortions of the 2 points are not in phase with the flowing medium. These distortions can be measured as a phase shift between the left sensor A and the right sensor B. Both sensors experience the same movement but at a different time. The phase shift is directly proportional to the Coriolis force, which in turn is proportional to the mass flow. Now you have a perfect direct measurement mass flow meter. As we have seen, this principle can work with a single tube system. However, by applying 2 tubes referencing each other, we can produce much larger differential signals. One tube acts as a reference to the other and therefore does not need any external reference, for example, the tube housing. This makes the meter independent of outside vibrations. Overall, a double tube meter shows a much better accuracy on both mass flow rate and density measurements due to the stronger signal, a much better turn-down ratio, and is less sensitive to behavior to external noise sources. We will talk in greater detail later about the differences between single straight tube and double tube designs. I would like to present this basic idea in a different perspective. The tubes oscillate without any phase shift in case of no flow. If there is flow in the meter, the tubes oscillate with a phase shift as previously described. This phase shift is directly proportional to the mass flow rate. The tubes are driven at their resonance frequency with an electromagnetic driver coil in the center of the meter, blue arrow, similar to the coil arrangement found on a loudspeaker. The phase shift is measured by two sensor coils at the apex points of the meter, gray arrows. The electronic converter drives the central driver coil with an excitation current, and the sensor coils give information to the converter about frequency, amplitude, and phase shift. The main advantage of Coriolis meters is the fact that whilst pressure and temperature may affect the volume of a given liquid, they have absolutely no effect on its mass. This metering principle is therefore independent of pressure and temperature changes. Since the meter does not require any conductivity of the medium for it to function correctly, it is one of the most flexible flow measurement principles which can be found in modern-day process measurement.